Welcome back, everyone, to this explainer. So let's just jump right in. Today we're looking at a completely fascinating connection between a gritty, low-tech environment from over 100 years ago and the literal bleeding edge of modern cloud-based AI. You're probably wondering, how on earth does a 19th century coal mine have anything to do with keeping today's most advanced AI models accurate? Well, you are in exactly the right place. We're going to see how the incredibly clever ways humans used to detect invisible threats back then are the exact same principles developers are using right now to protect our digital world.
Section 1. Canaries in the coal mine.
Okay, to really understand how we protect AI today, we first need to take a quick step back in time. Picture the 19th century. Thanks to the massive boom in train travel and steam engines, the demand for coal was absolutely skyrocketing. But, this boom came with a pretty terrifying cost. Miners were suddenly being forced to dig way deeper into the earth than ever before. And as they did, they ran into a whole new world of deadly, toxic gases and the constant, looming threat of explosions. They desperately needed some sort of warning system. Enter John Scott Haldane. Born in Scotland back in 1860, Haldane was a brilliant physiologist, and he actually went down into these dangerous coal mines himself to study respiratory physiology. By the early 20th century, he took all of that research and introduced a brilliantly simple, totally life-saving innovation, using canaries as an early warning system in the mines. His work was just so profound that it literally laid the groundwork for modern occupational medicine.
So the absolute worst threat these miners faced was something they called choke damp, which we know today as carbon monoxide poisoning. The terrifying thing about carbon monoxide is that it's a completely invisible, odorless killer. You literally have no idea it's there until it's too late. But Haldane knew that canaries have incredibly rapid breathing and a super high metabolism. This made them vastly more sensitive to this toxic gas than humans. If a canary in a mine suddenly stopped singing or worse, collapsed, it was the ultimate immediate red alert. It meant evacuate right now. It was a biological sensor, plain and simple, and it saved countless lives.
Moving on to Section 2. What are synthetic transactions?
All right, let's fast forward to the present day and see how this all connects to our modern tech landscape. Out in the modern cloud, AI models face their very own invisible, odorless threat. It's called model drift. Basically, it's this silent, sneaky degradation in a model's accuracy, performance, or availability over time. And just like those miners needed a sensor for gas, AI developers absolutely need a sensor for drift. Today, that brilliant modern sensor is called a synthetic transaction. Security experts like Eric Conrad and his colleagues define this as the creation of automated scripts or tools that perfectly simulate the actions a normal user would take in an application. They're scheduled operations that mimic human behavior to establish expected performance norms. In the AI world, these automated scripts are our digital canaries. They proactively check, hey, is the AI still accurate? Is it fast? Is it online? And they alert us to that invisible model drift before it causes any real damage to the user experience.
Now you might be wondering, why not just keep an eye on actual users? Well, here's the thing. Real user monitoring relies entirely on live, unpredictable, and frankly, chaotic user interactions. By doing that, you're essentially just waiting around for a user to stumble into an error. Synthetic transactions, on the other hand, give you controlled, consistent testing on a perfectly scheduled interval. You aren't waiting for a customer to have a terrible experience to finally realize your AI is broken. Instead, you're testing it systematically, constantly, right there behind the scenes.
Which brings us to Section 3. Benefits of the automated framework.
As an AI model scales up to handle more content and a lot more users, you just can't run these tests manually anymore. You really need a dedicated, automated framework. And building this kind of architecture brings 4 massive advantages to development teams who are trying to maintain peak performance. First up, proactive identification. By simulating queries against a known baseline, developers can catch model drift, accuracy drops, and lag instantly. It ensures continuous, smooth service. Second, consistency and control. It gives you this reliable, repeatable environment to test very specific pathways. Third is performance benchmarking. Say you update your cloud infrastructure. Well, these tests instantly tell you if that update accidentally wrecked the AI's speed or accuracy. And finally, a global perspective. You can run these synthetic transactions from servers literally all over the world. That ensures a user in Tokyo is getting the exact same high-quality uniform experience as a user in London across multiple different languages.
Section 4. Implementation Challenges.
Now, I want to be totally clear here. Setting up this system definitely has its hurdles. Building a robust fleet of these digital canaries requires some pretty meticulous planning, and teams run into very specific operational challenges. Take maintenance complexity, for example. AI models are highly dynamic. They update constantly. That means your testing scripts require continuous, expert attention just to keep up. Then, there's the whole issue of high operational costs. Because these synthetic scripts are pinging the AI in real time, they burn through some seriously expensive computational resources, specifically GPUs. You also have to deal with limited coverage. Your scripts only test the paths you predefined, right? So they might completely miss weird edge case scenarios that real users inevitably invent. And finally, evolving user behavior. You have to constantly update your scripts so they accurately reflect how people are actually interacting with the technology day to day.
To really cement how this automated consistency works, despite all those challenges we just talked about, let's think about a fantastic analogy. Imagine a night security guard with a flashlight walking through a massive facility to make sure all the doors are locked. For that guard to be effective, they have to walk the exact same route every single night to ensure total uniformity. Well, that is exactly what a synthetic transaction is doing. It's essentially automating that security guard's patrol. It guarantees repeatable results and a safe, secure experience for the end user every single time.
Section 5. The detection phase.
And that brings us to the broader picture of AI lifecycle management. Specifically, in the detection phase of the 6D framework, you have to defend your model continuously. And we do this by combining our tools for maximum defense. When you layer RLHF, which, if you're not familiar, stands for Reinforcement Learning from Human Feedback, with the automated vigilance of synthetic transactions, organizations can create an incredibly robust system. Think about it. You have the nuanced, expert input of human feedback perfectly integrated with the tireless automated simulation of user interactions. Together, these techniques fortify the AI against model drift. They allow the system to adapt, evolve, and truly excel when it's out there in messy, real-world scenarios.
Which leaves us with this final thought. Just as John Scott Haldane completely revolutionized industrial safety by understanding his environment and introducing a really simple practical sensor, today's developers have to use that exact same scientific ingenuity to protect our digital infrastructure. So I'll leave you with this question. How will you deploy digital canaries to protect your AI models from invisible drift? It's that commitment to continuous improvement that ensures our AI doesn't just survive, but actually thrives in an ever-changing environment. Thank you so much for joining me for this explainer, and I really hope this sparks some great ideas for your own projects.